Good morning, everybody. I'm excited to be here with you today. Um, I recognize lots of your names from the workshop we did a couple days ago, a couple days ago, a week or so ago, on just general how to use R. So today, we're doing my favorite part of using R is data visualization. Mostly because you can make really pretty cool things using R without having to draw anything by hand. And so you make like cool looking things, but it's also really, really essential for communicating your results, for communicating policy, for convincing um, bureaucrats and lawmakers about your findings. And so it's really important stuff that we're going to be covering today. Um, so we're going to be doing a lot with R. If you were with us in the last session, what we did is we did a whole bunch of stuff with RStudio Cloud, where I would talk about things with slides, and I would turn it over to you to have a turn and to actually type some code and run some code. We'll be doing the same thing today. So I will have a link in a couple minutes that you can join the RStudio Cloud workspace, and you can have a project that you can work with all of the data and everything you need there. So pay attention to that. And so let's go ahead and get started. Also, all these slides are going to be available. They're currently in RStudio Cloud once you join the workshop workspace for today. But they're also online, and so you should be able to just use a link to get to them, and I'll show you that link in a bit. So all of this stuff in a little bit. But what I want to do first is ask you all this question here. Why do you want to visualize data? And this is an important question because I've been doing lots of these workshops and teaching lots of R classes. And for some reason, data visualization is always everybody's favorite topic. When you ask people why they want to learn R, they'll say that it's because of data visualization. That's like all. It's not because of modeling. It's not because of stats. It's because of visualization. So what I want to know is in the chat or in person via voice or whatever, I want you to write out kind of why you care about data visualization, why you actually came to this workshop this morning, and what you're hoping to learn, and like why do you even care about visualization? So go type. Okay, so I'm liking these comments here because you all care about communicating data and telling stories, and looking at complexity and looking for understandability. This is all excellent stuff. This is exactly why we visualize data. Because humans suck at looking at numbers. We are visual people. We've evolved over millions of years or whatever to look for patterns out in the world and do stuff with those patterns. It's really, really hard to see patterns if we just look at like raw numbers. That's meaningless. Even if you've been studying statistics for years and years and years, when I look at a regression results table in an academic paper or in a report, and it just has a whole bunch of coefficients, I just stare at it, and it takes a long time to figure out what's going on. But if you can convert that into something that's graphical, then like I understand it a lot faster, and then the general public also understands it a lot faster. And so it enhances the ability to communicate. As Katisha says here, it lets you turn meaningful information or turn data into meaningful information that can inform decisions. And I fully believe in that. That's exactly why I teach this stuff. That's why I care about this stuff. Because we want to kind of change the world, change policy using visualization. Kind of the best example of this that we've seen over the past few months um, of a visualization that's had a powerful effect on policy is this whole idea of flattening the curve. So if you remember back in like March, when COVID-19 was first becoming a thing, there was a graphic that The Economist published and a couple other places published that wasn't based on actual numbers. It just had a density plot that was really, really tall that showed what would happen if we didn't have any lockdowns or anything, and then hospitals would go over capacity and lots of people would die. But then the flattening the curve example is if we have protective measures in place with social distancing and masking and other things, then the curve goes flatter. And so even though I'm not an epidemiologist and most of us are not, um, flattening the curve became kind of this very popular rallying cry for shutting down things and for trying to curtail the pandemic. And that was all based on a simple data visualization that wasn't actually based, like there were no numbers behind it. But the concept was still there, and it allowed people to communicate very clearly kind of this policy proposal to stay home and flatten the curve. So this does have like real world consequences. We care about this stuff. So in the world of stats, though, for whatever reason, there's been some reluctance to look at data and to visualize data. Some statisticians who are purists about this don't ever want to look at their data. They just want to see the raw numbers, and they'll figure it out with the raw numbers because they don't want to be swayed by any false patterns they might see, or somebody trying to tell a story and having an angle or bias or whatever. And so there's still today, some people lean towards never looking at the data and or never looking at pictures of the data and just looking at the raw data itself. So as an example of this, imagine you have some data set that looks like this. It has an X column, it has a Y column, you've measured two things, and you just want to see if they're related. Maybe you're interested to see if X causes Y, or if X is associated with Y or something. So in R or in SPSS or whatever stats program you use, you look at the first few rows. Neat. You can look at that and see if there's patterns. It looks like Y is higher than X, I guess. Sure, but this is just the first 10 rows. It could change later. So then you run some simple summary stats and you look at the average for X, the average for Y, and the average or the correlation between the two. And let's come back here. And you see that X is actually a little bit higher on average than Y, so neat. And there's not really any correlation between them. It's kind of a negative 0.06, which if you remember from stats, that's basically zero. So you can conclude there's no correlation between the two, and you publish this paper and say, hooray. The issue with this, though, is this average and correlation here looks different if you actually plot the data here. This right here, this is 12 different scatter plots that have the same mean and standard deviation and correlation between X and Y. And the fascinating part about this is your relationship could be any of these. It could even be the dinosaur here at the end, right there. And so without looking at the data and seeing what the relationship actually is, you can be left with like trying to report about a dinosaur relationship. And so maybe the overall effect you see is like slanting down or slanting up, or it's a circle or a star or a dinosaur X shape. All of these are completely like they have the same average, same standard deviation, same everything, but the relationships beneath them are wildly different. And so without visualizing this and without looking at it, you're going to start telling incorrect stories, and you're going to mislead people and mislead yourself. So it is very, very important to look at your data. And then just beyond just looking at it and saying, oh, this is what the relationship looks like, use the stuff that you look at to then communicate that story. Just showing numbers in a report is not going to be super helpful to your audience. Having a picture of your findings is a lot more memorable. So we care about pictures. So with that foundation of like, we actually care about this stuff, go ahead and go to this URL here. And this will open up the RStudio Cloud instance that we'll be using for today. I'll also put it in the chat here, so you can just click on it if you want. So this will open up an RStudio Cloud workspace for you. Wait for a minute or so it can load and start and get ready. And then you should be able to follow along for the day. So what we're going to be doing is continuing kind of the philosophy of data science and analysis that we talked about in the previous session, which comes from this book here. This book, R for Data Science. It's free online. I recommend, if you're interested in this R stuff, follow this. Chapter 3 in this book is all about data visualization. It covers everything that we're going to be covering today. And so definitely go check this out. The analysis pipeline that this book proposes looks like this. And we talked about this in the last session about the tidyverse here, where if you want to do any sort of analysis with data, you generally follow this pattern here, where you import data, you clean it up, and then you go through this process here, where you transform the data, you model it, and you visualize it. And then you transform more and model and visualize, and you're kind of in this cycle here of analysis. And then when you're done, you communicate. So what we did last time is we went over each of these steps just very briefly, showed you how to import data, how to clean it up, how to make basic graphs with it, how to transform it using dplyr with like group by and summarize and other functions that let you take really complex data and narrow it down to something usable. And then we showed you how to communicate that using something called R Markdown, where it lets you mix code and text. So you can just type a regular report and then say, here's a table, and then you have the code that generates the table. And then you can say, here's a picture, and then you have the code that generates the picture. And everything is just built into the same document, which is really convenient for analysis, because you remember where the code for making all your tables and figures is, because it's right there. And everything's just kind of in a single document. So what we're focusing on today is just this visualize part here, because it is exceptionally important. If you come to the final session of the Georgia Policy Labs workshops, we will be talking more about models and how to model data and look at things like difference and difference analysis, regression discontinuity analysis, things like that. So keep that on your calendars and come, because you'll find really fun, interesting things there. But yeah, the goal for today is the visualize side of this cycle here. So the plan for today, after this little introduction, we're going to talk about this core concept in visualization called the grammar of graphics, which is a language that you can use to describe data-based graphics. That's what the GG in ggplot stands for. ggplot is an R package that lets you make fancy plots. The GG stands for the grammar of graphics. It's a book that somebody wrote describing how you can explain what graphs are using human language. And so ggplot is just the R implementation of that. Then we will talk about some basic graphic design principles and how that gets applied to plots in ggplot. And I will teach you a fun acronym here, CRAP, which is actually crap, but it lets you make non-crappy things. It makes you make beautiful graphic designed things. And then for the last part of the session, we'll talk about interactive visualizations. And how you can kind of extend the basic stuff that you know how to do in ggplot to make animations and to make interactive plots. And it's actually fairly easy once you understand ggplot itself to suddenly make an interactive HTML graphic or to make a movie showing visual or showing different parts of your graph moving over time. So it should be fun and exciting. At the end of this section of slides here, I actually have a whole bunch of extra resources you can follow. If you get the slides from the RStudio Cloud workspace, you'll see all these there too. There are these two books here by Kieran Healy and Klaus Wilke. They are both free. There's a physical version of each that you can buy, but they also have an online version for free. They're basically like textbooks on how to use R to visualize data. I recommend them highly if you're interested in this. I also have an entire online course for free with hours of video and interactive code and all sorts of things there that is just focused on ggplot. So again, if you're interested in this, I'd recommend going there, following through the course and figuring it out. You can do really cool things. The rest of this are just a whole bunch of different books that are useful for data visualization. I also have some resources about graphic design, different links for fonts and colors and other things like that. And then for those of you interested in storytelling with data, I also have a few videos and books about how to tell better stories. And we'll talk about some of this stuff later today too. But these are some helpful resources you can look at later. I highly recommend it. So let's go ahead and get started with the grammar of graphics. So if you haven't yet, make sure you go to this URL so you can open up RStudio Cloud and follow along. So go ahead and in the chat, once you have RStudio Cloud open, just say like, okay, or yes, or some sort of acknowledgement that you are ready to go. All right, so in RStudio Cloud, you should see something that looks like this with different panes. So just as a really quick review, if you weren't in the session last time, or if this is your first time looking at RStudio Cloud, this area of the window here is called the console. This is where you actually type stuff and have it run in R. So if I type 2 + 2 here, it should say 4. Hooray. That's like the go-to test code. It works. It knows that it's 4. Down in this corner here, you have the Files panel. It shows all of the different files you have access to on the RStudio Cloud server here. These documents here, these RMD files, these are R Markdown files, which lets you mix code and text. If you click on this first one, 00 links to slides, these are the links to the HTML versions of all the slides that I'm doing that we have for today. So if you look, here's the introduction slides. So that's what we just went through there. So you have links to the actual ones on the internet. You can also click on the slides folder right here and download PDFs of the slides. They're also there too. Because R Markdown is such a powerful way of communicating and mixing code and text, you can actually make entire like PowerPoint-like presentations using R Markdown. So all of the slides for today are actually R Markdown files. You can actually look at them and see the code that generates the examples on the slides, which is pretty cool. So you have access to all of that too. And then there are some cheat sheets here with different, a few different PDFs here explaining just kind of a brief overview of how to do things with ggplot and how to do things with themes and other things like that. So that's kind of what's here in RStudio Cloud for today. So let's go ahead and get started with the grammar of graphics. So this is the slides named 01 grammar of graphics. Okay, so this idea of the grammar of graphics, as I mentioned in the very beginning, is based on this book here by Leland Wilkinson. He wrote it in the early 2000s, late 1990s, called The Grammar of Graphics. And in this book, he lays out a way of describing data-based graphics. And he invents a special term that we'll be using throughout the day that is really, really important. It's this idea of an aesthetic. This is confusing because generally when you think of aesthetics, you think of like pretty things and beauty and style and fashion and things like that. That has nothing to do with this in the graphics world, in the data graphics world. Aesthetics are the visual property of some graph. So the size of points, the color of points, the fill of bars, the position of points on a page, all of those things are aesthetics. They're graphical elements of some data-based picture. So that's what we're talking about when we say aesthetics. Data, on the other hand, hopefully that's familiar to everybody, it's really just a column in a data set. And so the magical thing about the grammar of graphics is that it lets you take columns in a data set and represent them using some sort of aesthetic. So you essentially map the data onto the graphic using an aesthetic. So if you have a column that shows like the population of a county, you can map population onto the size of points or onto the color of points. And then all of your points will be sized differently or shaded differently depending on the population of the county. So that's where we're taking a column, mapping it onto some graphical part of, or some visual part of the graph, and then representing what is in that column visually. So that's the whole secret to this grammar of graphics idea, is you're taking data in a data set and somehow showing it graphically on a page. And so that's kind of what we're going to be working with today, is how to do this the best way. But what I want to do first is we'll turn it over to you. We'll take about 5 minutes here. I want you all to go to this URL here. I will stick it into the chat too, so you can just click on the link. This is a 4-minute YouTube video. So I want you all to watch this video. And as you're watching it, I want you to make a list of all of the variables that are being shown in the graph. So think about what columns might be in a data set, and then make a list of how those variables are represented in the graph, how they are shown graphically. So go ahead and do that. You have about 5 minutes to watch the video and make that list, and then come back and we will talk about what you found. So 1, 2, 3, go. All right, time is up. Um, wasn't that a fun video? So Hans Rosling was a really cool guy. He cared a lot about public health. Had a PhD in statistics. Was based in Sweden, but got famous all over the world. He has a longer, 18-minute long TED talk that he did that initially got him famous, where he walks through the same 4-minute thing that you just did, but kind of an extended version of it. He wrote a book a couple years ago that was published, and is all about kind of how all of the great public health strides that have been taken over the past few centuries, which is really cool. He unfortunately died a few years ago of cancer, but the stuff like his work here that he started trying to show public health data in a really accessible way has kind of taken off and has changed the landscape of data visualization based on this here. It's actually made animated graphs a lot more popular, and people love using them now because he did that. He was able to kind of move those dots around, and it's kind of a really cool way of visualizing and communicating data. He started something called the Gapminder project. I don't know why it's called that specifically. It has an about page somewhere, but they make all of that data that you just saw available. And so if you were around for the last session, we used a data set called Gapminder. It was based on his data. We'll be doing a little bit more of that today using the Gapminder data just because it's super helpful. It's clean data that his team has been able to filter down, so it's easy to work with. So what I want now is in the chat, I want you to all list the variables that you found in that graph. So go ahead and type or paste or whatever into chat this first question here, the variables that are shown in the graph. So what columns might be in Hans Rosling's data set before his graphics team did all sorts of fancy things. Okay, so country, income, lifespan, life expectancy, average income, population, country, continent was in there, and year was in there. So that's like 5 or 6 different variables that he had in there, which is cool. How were those things shown graphically? How were those different columns in the data set represented in that picture? So go ahead and type that into the chat as well. Okay, so we had size and color and location. So the size of the different dots was population. The color of the different dots was continent. The position of the dots on the x-axis was life expectancy. No, it was GDP per capita. And then on the y-axis, it was life expectancy. You all mentioned year was represented in the plot. How was year shown? So the big number up in the top corner. How did the data respond to that? Because you can just put whatever label you want. And so how were you able to see changes across time? The animation, yes. So we actually mapped the year column onto motion and animation, which is really cool. That's kind of the revolutionary part about his graphic here, where instead of just having a static thing on a page with an x-axis and a y-axis and size and color and stuff, they actually mapped the year column onto time and onto actual animation, which is really cool. So yeah, that's everything in there. I'm here with Hans Rosling. So if you look at this chart here, this is basically what you all just discovered. There are these 5 different columns that were in the data set. The aesthetic, which is how they are shown graphically, are right here. You have the x-axis position, the y-axis position, you have color and size and time was one of the aesthetics on there. And then the geometry is how those things are graphically shown. So just because you're mapping color onto something, the something that you're mapping it onto can change. In this case, it was a point, but it could have been like a hexagon. It could have been a box. It could have been a box plot. It could have been anything that can that is graphical, but then it can have different colors or different sizes. So in this situation, it's all just points. And then the geometry here for showing year was just the animation, not really geometry. That's just kind of time moving is, I guess, the geometry. So you're really good at recognizing aesthetics and geometries. That's great, which is nice because once you understand this difference, if you can look at a plot and say, I recognize these graphical elements, and I recognize these aesthetics of the graphical elements, meaning this column is mapped onto this point, or mapped onto this bar, or mapped onto this box plot. Translating this into code for R is actually fairly easy. So this same chart right here, this is the R code version of it. In ggplot, there's a function called AES, which stands for aesthetics. And so here we have an X aesthetic, a Y aesthetic, color, size, and then this last line here is for the animation stuff. It's a separate package, but you essentially have a transition aesthetic. And then you use some sort of geometry or geometric shape to represent these aesthetics. And so in this example, these were all just points. So it was just using geom point, and then that was able to show the X and the Y, and then coloring the points by continent and sizing them by population. And so the R code for translating this aesthetics and geometry into code, these are basically identical, which is really nice because it makes it easier to write this code. It maps very well onto English. So the general template for using ggplot, and you'll get lots of experience with this, this is generally what you do in R. You use the ggplot function, you feed a data set into ggplot that has a whole bunch of columns in it, and then you use different functions after it using the plus sign here, and you can layer multiple functions on, where you say, I want to specific aesthetics in the graph to specific columns. So here you would say X equals something, Y equals something, color equals something. And then it gets shown as some sort of geometric shape. So that's the general outline or the template that you have. You have to feed it data, you have to feed it mappings, and you have to feed it geometric shapes. So Hans Rosling's graph here would look something like this. If you had a data set, this is just 2007. So we filtered the Gapminder data, so it's only looking at years that are 2007. The mappings here, we're putting GDP per capita on the x-axis, life expectancy on y, coloring by continent, and resizing by population. And then that actually gets shown on the graph as a point. And this will create that same Hans Rosling graph. It just won't be as fancy as animated, but it'll be the same thing. And so another kind of slower example of this. So if you imagine a data set that looks like this, with these countries and continents and these other columns here, again, we're just saying take this continent column, map that onto color. Take this population column, map it to size. Take life expectancy, map it to Y. Take GDP per capita, map it to X, and show it using points. And if you do that, you get a graph that looks like this. So that is the same Hans Rosling thing, just with uglier colors and not animated. So we have a good question here from Jonathan Smith. Is the geom function the type of graph, like a scatter plot or a bar chart or a pie chart? Kind of. The nice thing about the grammar of graphics is that it actually is a whole language for describing pieces of a graph. And so when you're using something like Excel and you want to make a specific plot, you have to click in the menus and search around for the exact type of plot you want. If you want a side-by-side bar chart or a stacked bar chart or a pie chart or something like that. So you want the specific chart type. With ggplot, there's not really a notion of chart types. So this happens to be a scatter plot because it has an x-axis and a y-axis that are continuous, and it has points that are going in between, like showing both x and y. But we didn't say like geom scatter. We just said geom point. And so it's really just showing these points here. That will change, like if we had an x-axis here that had, instead of continuous numbers, it had categories, like if we had each continent here, and then we had life expectancy on the y-axis, we wouldn't get a scatter plot. We would get a whole bunch of points within each of, like we'd have a almost type of column here for Europe and one for Africa and one for Asia, and you'd have a whole bunch of points within that column. And so we didn't change any part of the code to say like make it not be a scatter plot. You just said we're still representing this stuff as points, but instead of having a continuous GDP variable on the x-axis, we're going to have it be a categorical variable on the x-axis, but still show them as points. A or a pie chart, for instance. In the ggplot world, you can make pie charts, but there's not like a geom pie. All a pie chart is it's a bar chart that is stacked. So it has all the categories kind of stacked in a line, and then it's twisted in on itself. And so there's a layer you can add in ggplot that makes the plot kind of twist into a circle. So that's all you're doing. Like a pie chart is just a bar chart that is twisted into a circle. And so the same thing happens here. If you want to make a pie chart, you don't say geom pie, you say geom col for column. And so you make a single column and then flip it. And so it's a different way of thinking about this. But it's, again, like it's this separate language that we have for describing graphical elements. And we'll talk about this later as you get more practice with this, of how to describe an actual graph using this grammar of graphics, rather than just saying, I want a scatter plot or a strip plot or a bar chart or things like that. You have a richer language for describing this stuff. Cool. So the different aesthetics that you can use, these are kind of the standard ones. You have color, you have size, you have shape, you have fill, and you have alpha. And alpha is transparency. And so an alpha value of 1 means totally not transparent, like that's here. An alpha value of 0 means it's completely invisible. So 50%, 0.5 would be something like this, where it's kind of half and half. You can kind of see through it. This is probably 0.2, 0.25, something like that. So those are the different aesthetics you can have. If you notice, there's a little bit of a difference in the color aesthetic. If you have discrete colors, like categories, like a continent or something, then the colors that will show up are going to be wildly different from each other. And that's by design. So you can readily tell the difference between A and B and C. If you have a continuous variable mapped onto color, then what it's going to do is do a gradient type thing. Because here, like this might be population, so it's going to get smaller and then bigger. And so you want to have one color that kind of shows that, that change as you move that variable up and down. And so that's kind of the different aesthetics you have to work with here: size, shape, fill, alpha, and color. Once you get into the animation world, time is kind of one of these, but it works slightly differently, as we'll see later today. Okay, so what we're going to do is have some fun making some graphs. But to do this, before we start doing the your turns, I need to quickly introduce this fun data set we're going to use. It was just released a month or so ago by some scientists who study penguins. And so this is a data set about 3 different species of penguins: the chinstrap penguin, the Gentoo penguin, and the Adelie penguin. And so what we're going to be doing with this data set, it has a few different columns about like penguin weight and flipper length. Hopefully those are fairly obvious. Weight is like the actual weight of the thing. Flippers, these are flippers. But then it has a couple columns about bill length. So on a penguin, I learned a month or so ago when I came across this fun data set, they have bills. So the bill length is like the length of the bill from like up here where it connects to their head to the tip. The bill depth is essentially the height of the bill, how tall the thing is. In actual like bird language, they call it the culmen instead of the bill, but we're just going to call it a bill because I've never heard of the word culmen before a month or so ago when I discovered this data set. So that's what we're working with here is bill length and bill depth, and then weight and flipper size. So what I want you to, so let's look at this picture here. You're going to be manipulating this graph here in RStudio Cloud to change some of the aesthetics and possibly map other variables onto the graph here. But if you look at this just initially, you can see that the Gentoo penguins generally have longer flippers and are heavier. So they're the bigger of those 3 types of penguins. The Adelie and the chinstrap penguins are kind of down in this range. They're very, very similar, but you can see there's kind of a big split here. The Gentoo penguins are bigger. And if you look at the graph code, it follows that same template. We're using the penguins data set. With the mapping here, we're putting flipper length on the x-axis, we're putting body mass on the y-axis, and we're coloring by species. So what I want you to do now is go to RStudio Cloud. There's a section called Your Turn 2. I want you to play around with the graph and add different shapes or different aesthetics. Right now you have color equals something. Change that to shape, change that to alpha, add a second aesthetic, add a third aesthetic. If you want to map one of the other columns instead of body mass, do something else and see if you can find some other relationship there. And so just play around with it, really. I forgot to put the timer here. I'm going to give you about 6 minutes to just play and see what you can find. So let me show you how to get started. So if we click on the R Markdown file here for 01 Grammar of Graphics, if you run this very first chunk at the beginning, that will load the Tidyverse library, and it will load the Penguins dataset. And if you click on the Penguins dataset here, it will show you all of the data here. So you have bill length, bill depth, you have flipper length, body mass, you have the sex of the penguin, and then their species, and then the island they were found on. There's like 3 different islands, I think, in here. So if you scroll down to your turn 2 and just click on the play button, that will make that same plot that we just saw. And then your job now is to just experiment with that, to change color to alpha, change color to shape, add something else in here, say shape equals island or something. Just play around with this and see which different kinds of graphs you can make. And again, this is all in this 01 grammargraphics.rmd file. And so I will give you about 5 minutes now to just play around with it and see what you can make. So 1, 2, 3. Okay, that's a good question. When do you use this plus sign? So in ggplot, and we'll show more examples of this in a minute, what you're doing is you're taking different layers and adding them on top of each other. So here we're just adding one single layer, the geom point layer. If we wanted to add another layer, then we would add a plus sign at the end of this and then add another layer and then another layer. So it's really just letting us layer different parts of the graph onto each other. This initial part, this ggplot section, that is just kind of the initialization of the graph. And so like this is just saying, use this data set, this penguin's data, and then start adding stuff to it. How do you plot for a subset of data, only the female penguins? So if you were here for the last session, we talked about manipulating data using something like dplyr, using the filter function. And so that's generally the easiest way to do a subset here. So what you would do, here we're plotting penguins. If we wanted just female penguins, we could make a smaller data set. We could say female penguins. And then we use the backwards arrow thing. The way you type that is Option minus or Alt minus on Windows, and that lets you make a new variable. So we're going to take the penguins data, and we're going to actually filter the penguins data so that sex is equal to, and I can't remember what's in the column, it is lowercase f, so equal to female. So now if I run that, you'll see that we have a smaller data set here that is just called female penguins. If you click on it, you can verify that this column is just female all the way down. And then here, rather than saying plot the penguins data, we can plot the female penguins data. And then there's the plot for just the female penguins. So the general process you go through is you take your data, you clean it up, you filter it, you do whatever you want, and then you plot that. So we have this larger data set of penguins, and then if we want just a section of it, we filter it, we clean it up so it's just this, and then we plot that. So hopefully that answers your question there. So yeah, like dplyr and ggplot work together. Dplyr is good for manipulating the data, and then ggplot plots the data. So that backwards pointing arrow thing is, if you're on a Mac, it's Option minus. If you're on Windows, it's Alt minus. Or if you're anti-keyboard shortcut, you do less than minus, and that's miserable. Don't do that. It gives, are you inside a code chunk? If you're inside the chunk where the actual code goes, then it shouldn't be equals. It should be that. If you're outside the code chunk, if you're just in the markdown area, it will give the equal sign. So unless there's some sort of preference that is forcing it to do that. Yeah. Okay, so what interesting things did you find? What different columns did you map onto different aesthetics? Somebody, if you're feeling brave, just copy and paste the code that you ran into the chat here and we'll look at it. We'll see what cool graph you made just by manipulating different aesthetics. Okay, so here it's shaped by sex. So you can see that there's a circle for female, a triangle for male. So you can see some patterns here. The heaviest Gen 2 penguins are all male. The females are lighter and have shorter flipper lengths. We also so it's colored by species, which is what we had before. And then we still have the same X and Y axis there. So we can find some cool, interesting things there just by sticking another column in into the plot. Did anybody do something else? What other cool things did you do as you were playing here? Let's try alpha. So alpha changes the transparency. We'll do alpha for like build length. Sure. Build length, mm. So what this will do, this will be the same graph that we had, but these points should be different levels of transparency depending on the bill length. So if we run it, so we have alpha equals, has to be spelled correctly. What do we call it? Bill depth. We'll do that one. That's the height of the thing. Depth, mm. There we go. So you can see that the Gen 2 penguins, they have a shorter build depth, I'm guessing, because it's more transparent. While these penguins have a taller build depth because it's less transparent. So you can kind of see that there. We could also size it by build depth instead. Cool. So kind of ugly, but it still shows the same patterns that these Gen 2 penguins have shorter build depths. These guys have bigger build depths. You can actually map multiple things at once. We can size by build depth, and we can do alpha at the same time. And so that way you get they're big and more or less transparent. And so just by manipulating these different aesthetics here and changing the Y and X, if we want to, so going back to the question about a scatter plot versus a not a scatter plot, let's, instead of looking at flipper or at body mass on the X-axis, if I take island, for instance, and put that on the X-axis, let's see what that looks like. So we'll say X equals island. There we go. So that's no longer like a scatter plot, but it's still showing that same data just using points here. And so you can see some cool things like these chinstrap penguins only exist on Dream Island, apparently. They don't appear on Bisco Island or Torgerson Island. And the Gen 2 penguins also don't exist on Dream Island and Torgerson Island. So you can see some cool patterns there. This isn't technically a scatter plot. This is something called a strip plot. But all we had to do to get a strip plot versus a scatter plot is we just changed what was getting mapped to the x-axis. We used a categorical variable instead of a continuous variable. The other magical thing is, if you notice, every time you add a new aesthetic, you get a legend automatically. It adds it here. You don't have to manually add any legends. You don't have to do anything. It just knows that it's going to put whatever aesthetics you have as a legend here, which is really cool. Later today, I'll show you how you can manipulate these. So if you don't want like these colors, or if you don't want those shapes, or if you want different levels of transparency, you can manipulate each one of these scales, is what they're called, for the aesthetics here. So you have total control over everything that shows up. But it's really good at just being as automatic as possible and as easy to use as possible. So hopefully that was fun. You got to experiment with just mapping different columns onto stuff here. One thing that gets confusing though is, let me come back to our Studio Cloud here. The aesthetics that you have here are also things that you can control manually. So let's switch this back not to island, and we'll get rid of size and we'll get rid of alpha. So we'll just look at these here. So here's that. Let's say we want all of those points to be bigger because those are fairly small. we already tried mapping one of the columns onto size, which worked. We got some of them to be small, some of them to be big. But what if we just want all of the points to be the same size, but a little bit bigger? If outside of this mapping section here, if we put a comma in between these two parentheses and then hit enter, then you can set whatever size you want or whatever color you want. So if I say size equals 4 and then run that, now all of the points are bigger. And that works because I manually set the size to some other value. If size was inside aesthetic here, then it's going to take one of the columns in the data set and map that onto size. And so each of the points are going to be differently sized. If you use the aesthetics, color or shape or fill or alpha or anything like that, outside of this AES function, then it will just be whatever you set it to. So if I want all of the points to be semi-transparent, I can come here and say alpha equals 0.5. I'm not mapping any of the columns onto it. I'm just saying make all of the points be halfway transparent. And now if you run it, you can see they're all halfway transparent. But the only reason that happens is because this one aesthetic is no longer inside this AES function. We're no longer mapping a column onto it. We are just manually setting it ourselves. And that is something that trips people up often. Just the tiny distinction between putting something inside AES and outside AES. So in this graph right here, the way you would make this plot, having all of the points be blue, is you would say color equals blue, but not inside AES, because you're not mapping a column called blue. You're just saying make all of the points be blue. So the difference here, this is what we have just been looking at here. We're coloring by species. So we're taking that species column and mapping it onto the actual colors. If we do something like this, though, notice how color equals blue is outside AES. And as a result, all of the colors are blue, or all of the points are blue. If you get that wrong, you'll end up with something like this, this first plot here. So notice how color equals blue is inside AES. And as a result, these points aren't actually blue, they're red, even though you get this cool legend that says this is blue. The reason that's happening is because it's inside AES. And so it thinks that it's supposed to map a column onto the color aesthetic. There is no column named blue in the data set. So what it thinks is that you just created a new column called blue, and it is blue all the way down. And so that's really what it's showing. It's saying that all of these points have the value blue in the magical blue column that you just invented that doesn't exist. And so it's just showing it as if it was sex or island or some other categorical variable. So that will be wrong. So manually setting any of your aesthetics, size or shape or color or anything, you need to do that outside of this AES function, because that is where the mapping happens. Anything that happens inside AES has to exist in your data set, and you're going to use the column name in the data set. Anything outside of it is just going to be however you want it to appear on the plot. Okay, so that's basically how you use aesthetics. Another important part about this is the geoms, the actual geometric shape that shows up. So these two plots here have the same aesthetics. They both have body mass on the x-axis, and they both have bill length on the y-axis. The only difference between these, again, talking about the whole grammar of graphics idea, the same underlying data, same underlying aesthetics. The only difference is the geometry. Here, we're using geom point. Here, we're using geom smooth, where it's drawing a smooth line between these two variables here. No data changed. The only code that changed is we switched geom point to geom smooth, and it took care of the rest because we're using this grammar of graphics idea. So if you remember this template that we've been talking about, we have the data set, we have the mappings. This geom function then is what we get to how we represent the different mappings. There are a ton of different geoms. There are dozens of these things, and people can create their own, and you can install our packages that have people's custom geoms that they make. Some common ones are things like geom point, geom call for columns. You can actually put text on the plot using geom text. There are things like geom box plot or geom violin. You can do histograms, the geom histogram. You can even do GIS type stuff with maps using this geom SF, and it'll do plots of geographic features, which is really cool. So if you look at the ggplot documentation, or if you just go to Google and search for ggplot documentation, you'll see this website here. And if you click on reference, it will have a list of all of the different layers you can possibly use. So if you look here, here's all of the different geoms that you can use in regular ggplot here. You have segments, you have smooth lines, you have spokes, you have violin plots, you have crossbars, you have all sorts of things. Geom hex, if you want hexagons instead of points. And each of these, if you click on it, it gives you example code and all of the documentation for it. So if you scroll down, it will show you here's geom hex with different numbers of bins. Apparently hexagons bin stuff. It's kind of like a histogram, but as a scatter plot type thing. And so there's all sorts of cool examples of different things you can do. Okay, so what I want you to do now is go down to your turn number 3. There is a strip plot or a scatter plot there. I want you to change it to a box plot. I want you to make this picture here. And if you look at the cheat sheet that I gave you in this folder here for ggplot, for data visualization, this first cheat sheet there, it has kind of a smaller version of this giant list of geoms. So I want you to look through the cheat sheet and figure out how you can switch this graph in your turn 3 to a box plot. So go ahead and do that. Make this picture. 1, 2, 3, go. And if you're really brave, add a second aesthetic. Fill it. So what we've been doing, we've been using color equals something. Box plots don't get colored. I think they might get colored. It'll be the borders. But if you want them to have like a full-on the color of the thing, use fill. So inside AES, say fill equals island, or fill equals sex, or fill equals something, and see what happens. Okay, so go ahead and wrap up your attempt. Let's show you what you do. All you do is you switch, this used to say geom point. We just switched it to geom underscore box plot. So rather than representing these things as dots, we're going to represent them as box plots. And that's all you have to do. The other aesthetics are the same. So it's going to have species on the x-axis. It's going to have body mass on the y-axis. We had a question of how to fill it with different colors. We can take one of the columns that we have in the data set, like species or island. We're already using species on the x-axis, so we can use island or sex, and we can fill by that. So in here, inside AES, we can say fill equals island. And now we'll get different, again, this shows that like the Gentoo penguins only exist on Bisco Island. The chinstrap penguins only exist on Dream Island, while Torgerson Island is like this happy place where all 3 penguins live, I guess. And so you can do that. We could also fill by sex if we wanted. So you can see on average males are heavier than the females. There are ways of getting rid of the NA. You would filter to get rid of all of the missing values. We're not going to worry about that for today. We can actually do both. We can say, or there's another aesthetic called line type. I think this will work. If we line type island, yeah, this is really ugly, but it works. You can see that there's dotted and dashed lines that represent the different islands. So you can see here, this gets really messy and awful. Don't do this in real life, but it's possible. We're just taking some aesthetic part of the graph, in this case, the line type, and we're mapping one of the columns onto that. So you can see the 3 different islands here, the 3 different, or male Adelie penguins on the 3 different islands are basically about the same weight, and the same thing with their female counterparts there. But that's really ugly in real life. Don't do it. Okay, so there's the answers here. So go down to your turn number 4. You're going to try something similar. This time I give you even less code. I just give you the initial ggplot data equals penguins. Your goal is to make this picture here, this histogram. So this histogram here just takes a count of how many penguins have specific bill lengths, and so it makes bins and counts how many penguins are in each of the bins. So go ahead and look at the cheat sheet, see if you can figure out how to make a histogram. You don't need a y variable because this count is not one of the variables in your data set. It will calculate the y for you. So go ahead and make this picture here. Make a histogram of bill length in turn 4. Okay, you have another minute or so. If you're brave and you've already gotten the histogram, try adding a white border to the bars. So you're not going to be mapping anything onto color. You're just going to say color equals white and figure out where you're going to put color equals white. It's kind of good practice with histograms to do that, so you can see the bin width, or you can see the bins a little bit better. Like if you look at this is just kind of a big blob of gray. But if there were white borders there, you'd be able to see it better. So see if you can figure out how to add a white border. And if you're super brave, see if you can figure out how to make the border be sized differently, either really thin or really thick. And so that's going to be using the size aesthetic, but not mapping it to a variable. So go ahead and try that too. Okay, so let's do it. So to make the histogram, we're going to use that penguins data. I'm just going to come here, zoom in a little bit. So we're just going to add geom histogram. We're going to say mapping equals AES. So we on the x-axis, we want something. That was bill length mm, and that should be all we need. That's that same graph that we saw. You'll notice it gave this message here. It's saying it's using 30 bins, pick a better value with bin width. That's because of how histograms work. It's really just taking the list of all of the different bill lengths and then saying by default, it's going to put them into 30 equally sized groups or equally spaced groups. But you don't necessarily want it to be 30. Like the actual width of this isn't going to be like from 55 to 60. It's going to be from like 60 or from 52.78 to 61 point something. Like it's not a very consistent bin width. So one thing, it'll always warn you if you don't do this, is if you do outside of AES, because it's not an aesthetic, you say bin width equals, and then choose some value. Let's try bin width equals 5. That's not the most helpful histogram here. This is just going from basically 30 to 35, 35 to 40, 45 to 50. But that's probably too wide. So if we switch it to bin width 1, now each of these bins represents one range of, or 1 millimeter range. So from 40 to 41, and then 41 to 42, 42 to 43, etc. And you can manipulate that and change stuff. I told you to be brave and try to add borders to the bars. The way you do that is you just say color equals white. And notice how, again, it's not inside AES because I'm not mapping one of the columns onto the color or to the fill. I'm just manually setting my own. And so now you get this nice white border around all of the bars. If you want those to be thicker or thinner, you can do that with size. Again, we're not sizing any of these bars by a variable in the data set. We're just saying size equals like, whoa, size equals 1. See what that looks like. That's kind of thick. If we go crazy, size equals 5, it's mostly just a white border now. If we go size equals 0.25, it should be a really thin white border. Neat. If you want these to be some other color, you can say fill equals blue. So now all of the bars will be blue. If you're familiar with HTML or web development, you can, instead of saying like the name blue, you can actually feed it a hex code. If you go to Google and search for color picker, it will actually give you this magical color picker. So if you want your own, let's say I want all of these histogram bars to be this color of purple, sure. If you notice, there's this hex code that it gives you right here. If I copy that And instead of saying fill equals blue, I paste that. So it's fill equals this magic incantation. If I run that, it's going to use that color. So that's how you can use, rather than these named colors, there's only a certain number of named colors that R has built in. But if you want whatever color you want, then you just use the hex code for it and it should show up. Okay, cool. So there's the code for it. We just did that. So let's do another your turn. This one's a little bit trickier. This time, instead of doing a histogram, I want you to do this density plot. And notice how there are 3 density plots. It's because it's filled by species. So go ahead and try to do this. Make a density plot of bill length filled by species. And if you're brave, make it so that they're semi-transparent, so that you can see through them, because this blue one is covering up the green. There might be some cool shape about the green behind it. So go ahead and figure that out. And then we'll go over the code. So go and ask any questions you have as they come up. Okay, so if you come back to RStudio Cloud here, here's the answer. We take so we have ggplot data equals penguins. We're going to add geom density, and then we're going to map with our aesthetics here. We're going to take the bill length, that's going to be on the x-axis, and we're going to fill by species. And then outside of AES, I added a separate alpha setting here so that they're all 70% transparent. And so you can actually see green has this weird bimodal thing behind it, the chin strap penguins. So there's some that are really light and some that are heavy, but there's nobody really in between. You can't see that because the Gen 2 density plot is kind of on top of it. But because we use transparency, that worked. And so that's how you would do it. If you didn't fill by species and you colored by species instead, you would get something that looks like this. It would just be the borders of the density plot, which looks neat, I guess, but that's kind of harder to see. So with densities, it's generally a good idea to fill. If we wanted to, we could get rid of the black border and we could say color equals white. See what that looks like. Cool. Kind of adds this 3D-ish looking effect where, because like the density plots are kind of layered on top of each other, and so it kind of cancels out the different overlap there. We can get rid of the border entirely if we say size equals 0. Now there's no more border because it's there, but it's not thick at all. So yeah, cool. If you didn't want to fill by species and you wanted to fill by sex, all you have to do is change that and it will automatically remap that column. If we wanted to fill by island, that was another one of our categorical variables. There's the 3 different islands with the penguins. And so again, all we're doing with this mapping is taking some existing column, showing it a different way in the plot. And so once you get the hang of this whole grammar of graphics idea, it gets really easy to just switch between different things. If we wanted to plot not bill length, but bill depth, all we have to do is change bill length to bill depth, and there's bill depth. So it's really quick and easy once you get the template, just switch different things in and out there. Cool. All right, so there's our answer here. So we've been doing lots of simple things, but you can also do more complex things by adding more layers. So if you look at this graph here, this shows the body mass and it shows the build depth and the relationship between them. And you'll notice there's this weird relationship here where the Gen 2 penguins are heavier and have a shorter build depth than these others. And so being able to see both the trends and the trends with the smooth lines and the points helps significantly. So we need to figure out a way to show both of these at the same time. We do have a quick question from Carol, where does size always affect the borders? And no, it depends on the geometric shape you're using. So in the case of this density plot, the size influences the borders. That's what the size is referring to. In the case of a scatter plot, the size refers to the actual size of the points. And so what is really helpful to do, and what you should get in the habit of doing as you're looking up like how to do different geoms, if you come to the help page and you search for something like geom point and look at it, it shows you kind of the basic template you're supposed to use. It shows you the different arguments you can feed it. But if you scroll down, there's always a section called aesthetics that tells you all of the possible aesthetics that you can use. So geom point uses X, Y, alpha fill, group, shape, size, all of those things. Anything that is in bold is required. So if you're going to do geom point, you have to use X and Y. It won't plot without those. You don't have to specify a color or a fill or a shape or anything like that. And in the documentation, it will tell you what these things do. So in the case of points, size refers to the actual size of the points. In the case of things like bars or histograms or density plots, the size refers to the border. And that it explains that in the documentation. So you just have to check to see what things get targeted by what. Which is important to do, especially as you start adding more and more of these aesthetics. Because if you look at this graph here, if you set a size aesthetic, for instance, it would change the size of the points, but then it would also change the thickness of that line. And you might not want that to happen. You might want only the points to be sized, and you might want the lines to be the same size throughout. You don't want them also to get thinner and thicker. And so it's good to pay attention to that, especially once you start adding more and more layers here. So with your turn, this is another your turn. This is a quick one. Go ahead and look at this code in your head and figure out what you think it's going to do, and then run it in RStudio Cloud and see if you were right. You have like 30 seconds to do it. It's fast. And see if your prediction was right. Okay, time's up. We're just doing 30 seconds, not a minute. So what we should have is a plot that has points using these different aesthetics here, colored by species, and then smooth lines also colored by species, which should look like this, which is what we had before, which is cool. So we have two different geometric layers showing the same aesthetics, and it works great. The only issue with this is this gets really repetitive to type AES, XY, and color, and then do the same AES, XY, and color. And that gets tedious. We don't want to do that. If you've also noticed, I didn't type mapping equals AES. You don't always have to do that. The reason why is because if you look at the help file for ggplot or any of these geoms, the first argument to ggplot is always the data set. And the second argument to ggplot is always the mapping. So you could just say ggplot penguins, comma, AES, put your aesthetics there. You don't have to explicitly say data equals and mapping equals. And in real life, when I do this, I don't say data equals and mapping equals just because that's extra typing. And saving typing is good because it reduces the chance of typos, which is what we want to do here too. So we could alternatively do something like this to get that same plot. Where if you notice here, rather than setting the mapping of the different aesthetics in these individual geom layers, we don't have to do that. If we put it up here in ggplot itself, everything will be accessible to all of the geom layers after that. So we can set the aesthetics once, and every geom layer that comes after it will appear, we'll use those. So that's what we want. That makes life a lot simpler here. Okay. Anything you set in individual layers, though, only references that single layer. So if you look at this, the only difference here, we're no longer putting color up here in the global ggplot thing. We're putting color just in geom point. So if you notice the difference now, before we had 3 different smooth lines. Here we just have 1 smooth line because we're only mapping the points. We're only mapping the species color to the points, not to the line. And interestingly, this actually shows us a statsy thing called Simpson's paradox, where if you look at the relationship between penguin body mass and build depth, it looks like it's negative. It looks like as you become heavier as a penguin, your build depth shrinks, because we're just kind of looking at the aggregate average there. But that's not actually the case. If you look at the 3 separate plots, it all goes up. It's just that we're aggregating, so it goes down. So fun little interesting stats tidbit there. So in practice, when I do this normally, I very rarely put mapping in the geom layers themselves, unless I want to narrow in on one specific, just have one thing be colored or one thing be filled or shaped or something. I put all the other aesthetics up in the global section here so that any layers I add after use those same aesthetics, and it saves a lot of typing. Okay, so this grammar of graphics idea, we've talked about three different principles here: data, aesthetics, and geometries. This whole grammar of graphics system uses what are called layers. So each of these different components are basically layers that you can add to some sort of foundational ggplot plot. So we took our data and then we added some aesthetics to it, and then we showed those aesthetics using geometries. Those are not the only layers that we have. We can do all sorts of things. So if you notice here, these are all the different layers that you can add to a ggplot plot. You can manipulate scales, coordinates, labels, facets, themes, and all of these do different things, and we'll talk about them briefly here. But you go through the same process. You take some plot, you add a geom to it, and then you add a scales layer, and you add a facet layer, and you add a labels layer, and you add these different layers to it, and it eventually builds up into a far more complex plot. Briefly, let me show you what that looks like in real life here. So if you look at this, for instance, here's a foundational ggplot function here. Then we're using this geom SF layer, which does geographic things. And so this is showing the Georgia map. And then we're using another geom SF layer where it's going to put points of all of the different public schools in Georgia. And they're all 0.75, they're all semi-transparent. It's colored by the number of students in the schools. So you can see like Gwinnett County, for some reason, has tons of people in their schools compared to other counties. And then you have these other scales where it's using a different coloring system and it's using a different theme. But it's the same idea. You're just taking these different layers of ggplot things and stacking them on top of each other. It can get really complex. If you look at this picture here, this has points. It also has labels. It has some annotations here. It has text and arrows. If you look at the actual plot, lots of this is commented, explaining what these do. But really, in the end, it's just here's ggplot, here's the aesthetics. We have an X and a Y, and then each of these things are different layers that we're adding on sequentially and just like layering it onto this picture until at the very end, this is really complex, you get something that looks like this, which is kind of magical. That's how all of this works. This is a similar thing. You take some foundational ggplot, here's the data set. We're mapping year and month to the x-axis, we're mapping some value to the y-axis, and then adding different geoms, adding different scales, adding different labels, and you end up with a plot that looks like this. So that's always the process you're going to be going through with ggplot, is just layering things on top of each other until you get your final great perfect plot. So we're going to talk about a few of these layers really quick. There are tons. Again, if you look at the ggplot documentation, you'll see examples of how to do all of this stuff. The point of this is not to show you how to do everything. It's impossible to do everything. If you go through the data visualization class I have with GSU, with all the different videos and stuff that are online, we spend basically class sessions dedicated just to facets and just to scales and just to each of these layers, so you get more practice with it. So scales, what they do is they change the properties of the variable that you've mapped. So if you added something that was like scale x log 10, we saw this with the gapminder data. That takes whatever is on the x-axis and puts it on a log scale instead of a linear scale. If you want the gradient, or if you want a gradient scale, you can do that. If you want to fill by this fancy palette called Viridis, we'll talk about this in a minute. It's perceptually uniform colors that are good for people who are colorblind, or if you're printing this on paper in black and white. This lets you change the actual colors of the fill or the colors or the points or whatever. You can set your own axis ticks. So if we said scale x continuous and then breaks 1 through 5, you're going to have tick marks at 1, 2, 3, 4, and 5 just on the x-axis. So that's what these scales things do. So here's an example of scale log 10. This is our gapminder data here. This is using the Viridis palette for color. So if you notice, instead of using this color system of like red-ish up to purple, This is going from dark blue to yellow, and it's different way of showing the colors there. So what I want you to do is go to your turn number 7. You're going to make the same density plot. If you want to, just go up and copy the previous one you made and paste it. But I want you to fill it using the Viridis fill scale. And so you're going to use scale underscore fill underscore Viridis and see what you can do. And if you're super brave, which you should be, look at the help file for scale fill Viridis, and you'll see that there are different options of the color palette. You can use option equals plasma or option equals inferno or other things like that. So go ahead and play with that for a minute or two and see if you can recreate this by adding a scale layer. Okay, so what I did here is previously we put the aesthetic mapping right here inside geom density. I typically don't like to do that because I just like to have it be up in the regular ggplot so it's global. So I have ggplot data equals penguins, and then we're putting bill length on the x-axis. We're filling by species, and then just adding geom density. If you select from the very end of geom density up to the beginning, so just those lines right there, and then press Command Enter or Control Enter on Windows, it will just run those 2 lines. It'll just run that selection. So you can see what it looks like just before you add any other stuff there. If we want this to be semi-transparent, we can say alpha equals 0.8, sure. So if we select this and run it, now you can see that they're semi-transparent. Hooray. So then the next thing we want to do is fill these using a different system. We don't want this green, blue, red stuff. So we're going to add scale because we're going to be manipulating the fill scale. So it's going to be fill underscore or scale underscore fill. And then we're going to use Viridis. And if you've noticed, you may have run into this as you were doing this. There's 2 different Viridis or 3 different Viridis scales. There's Viridis C and Viridis D. So Viridis C is for continuous things. If it was like an actual number ranging from 0 to 1,000 or something. And that's going to be slightly different from Viridis D, which is discrete, where it'll put things in separate categories. Like here, you have 3 different categories. So we want Viridis D for 3 discrete levels. So if you run that, you should get something that looks like this. If you want different palettes, so the whole Viridis world, we'll talk about this in a minute too. There are different palettes that come with Viridis. If you just Google Viridis, you'll see it. There's the default Viridis. There's also Magma and Plasma and Inferno that are just different color gradients here that range from yellow to blue or light orangish to black. So you can actually change the palette instead of using Viridis to something like Plasma. And the way you do that, if you look at the help file for Scale Fill Viridis, you'll see it has this option, and it uses these weird acronyms or like initials. I never remember what they are, but if you scroll down and see this option, you can either type A, B, C, or D, or actually write out Magma or Inferno or Plasma. And so if I come here and say option equals Plasma, then it looks something like that. Neat. If you want to specify your own colors, you can do that too. So rather than using scale fill Viridis, we can get rid of that and say scale fill manual. And here we can give it a list of color names and just have it be those. So what we have to do is say values equals, and then we feed it a list of 3 colors because there are 3 different possible species here. So in R, the way you do a list is you use the C function. We say C, open parentheses, close parentheses, and then we're just going to feed it a list of 3 colors. These can be hex colors that you get from Photoshop or from the internet. These can just be names. So we can say red and orange and blue. Okay, so with those 3 colors, it should show up red, orange, and blue, like that. Neat. So you can specify your own. You can specify one of the built-in Viridis colors. You can do all sorts of things. The main thing to remember, though, is we're using scale underscore fill because we're manipulating the fill aesthetic. If we had a color and we wanted to use our own colors, the only thing we'd have to change is scale color manual or scale color Viridis or scale color whatever. If you want to change the sizes, the range of sizes of the points, that would be scale underscore size underscore or something. So all of the aesthetics have scale functions that go with them that let you manipulate things. Okay, so there's the answer there. Facets. So what are the benefits of using scale fill Viridis? We will get to that in a minute when we get to the graphic design. There are actually perceptual differences in how people look at colors. And the nice thing about the Viridis scale versus like a rainbow scale or a gradient scale is your eyes can actually tell the difference between distances in the color spectrum that you can't with like a rainbow scale or just with whatever values you're throwing in. So it is helpful and more accessible. And I'll show a whole bunch of examples of that in a little bit. That's a good question. Facets. This is one of the most powerful parts of ggplot here, where you can make, so a facet is really just a subplot where you can take a plot and split it into smaller plots. And the nice thing about facets is you can actually just take a column in your data set and make facets based on that column. And so here, if we're looking at the Gapminder data set, for instance, if we add a layer that says facet wrap, because it's going to just make a whole bunch of facets and wrap them in a line. So if it runs out of room, it'll go down to the next row. If we facet by continent, what we will get is 5 different subplots, one for each of the continents, because there's a column in our data set named continent. So it's just going to split it into separate continents. You can actually facet by multiple things. If we faceted by continent and year, you would get a separate subplot for each continent and each year. So you'd get Africa 2007, Africa 2008, Africa 2009, etc. And so it's like a really cool way of looking at your data here. So here's, for instance, the Gapminder data set faceted by continent, also colored by continent. So you can see all of Africa is red, but it's in that subplot there. If you facet by both things at the same time, continent and year, you get subplots for the continents in 2002 and in 2007, which is pretty neat. So to do this on our own, we'll just do it together here because you don't have the code. It's just kind of archaic. You just have to memorize this. It's facet underscore wrap, and then use this vars function to tell it what variables to facet by because it's not quite an aesthetic. And so it's kind of a little bit different syntax. But if we take the scatter plot, if we go to your turn number 8 in RStudio Cloud, we're going to facet this plot by island. So to do that, we're just going to add another layer. We're going to say facet underscore wrap. And then we have to say vars for the variables that we're going to facet by. And the variable name was island. So if we do that and run it, we should get 3 separate subplots. And so we see again, the Gen 2 penguins only live on Bisco Island. The Chinstrap penguins only live on Dream Island. And Torgerson Island only has the Adelie Island, or penguins, while Adelie is across all 3, but Torgerson is just them, which is a pretty cool way of kind of subsetting your data. We could also facet by sex if we wanted, because that's one of the columns we have. And so there's the female and male, and then there's some missings that we could filter out. So yeah. Does the order of layers or faceting matter? It does sometimes. It does when you think about the geoms. If you have like geom smooth and geom point, that does matter. So if you do geom smooth first, it'll put a line down. And then if you do geom point, it'll put the points on top of that line. And so that does matter. You might cover stuff up. Like if you put geom point and geom density on at the same time, if you put the points on first and then the density on top, that would cover up a whole bunch of the points. If you put the densities on first and then the points, then you'll see them because they won't cover up the density plots. The other layers though, like faceting and scaling and labels and all of that stuff, that doesn't matter. That can go anywhere in the whole stack of layers. Typically what I do and what most people do is they'll do the geoms first. So they'll do all of the aesthetic setting and then the geoms. And then after that, it's just kind of a free-for-all. Some people will put themes next or faceting next or scales next or labels next. It doesn't really matter. But general best practice is to put the geoms first because that's good. Okay, so there's our picture there. So coordinates are also one of these layers. It changes. It basically lets you zoom in. So here, if you have chord Cartesian, you can say use the y-axis, but only from 70 to 80. So the data is still there. We didn't throw any of the data away. We're just zooming in just on 70 and 80 and just on 10,000 to 30,000 on the y-axis there. You can also do chord flip, and that will switch the y-axis and the x-axis. You could also just switch the y-axis and x-axis in the aesthetics, but you can also just flip it. That's fine too. Labels, you use this labs function, and that's how you add stuff to titles and captions and change the axis labels and things like that. So what you essentially get is something like this. Notice how we have labs, and then we have a whole bunch of different arguments in here for title, subtitle, X, Y, color size, caption. You can see where those all appear in this graph here. So we have title, subtitle, caption. The name over the different legends here is controlled by color and size here. So it lets you control all sorts of stuff. And then finally, there's themes. And we'll talk about this a little bit more in the next hour. But you can control every visual element of the graph here. So the default uses theme gray. So you don't have to include that. It's just going to happen by itself. But you can also use theme underscore BW, and that'll do black and white. You can do theme dark. And so this is that same gapminder plot, but all we did is add theme dark to the end. And then same thing here, we just added theme minimal. So if we go back to our penguin plot, for instance, with this facet here, we can just say theme underscore dark and run it. And now we have that darker theme. And that's great. Really hard to read. Probably don't use that in real life. Okay. There are all sorts of cool themes online. And so there's a package called GG Themes, for instance. If you want to make your graphs look like they came from the Wall Street Journal, you can. If you want to make it look like you did stuff in Stata, there are Stata themes. There's even like Excel themes if you want to make people think that you did this stuff in Excel. Official organizations generally make their own themes. Like the BBC has their own ggplot theme that they've developed, and so they just make a plot and then they say theme underscore BBC, and then all their stuff looks like this. So they use these colors, they use these fonts, everything's kind of spaced this way. This is the internal BBC stuff. And so that's kind of how you do this. There's also different ways of targeting specific theme elements. So if you use like theme black and white, that's a whole bunch of built-in stuff. But then you can also control specific theme, like fiddly things, like the exact position of the legend. You can make the plot title be bold. You can get rid of the grid. You can make just the y-axis title be italic. You can target all sorts of little tiny parts of the plot using this theme function. And we'll show that in a little bit as well. So before we move on here, a question from Katisha here. Was the year variable in the Rosling animation text or label aesthetic? It was text. The only difference between text and label in ggplot, they're both text. Label just has like a border around it. So if you look here, where was it? So these right here, these blue and red labels, those are labels. And then this is just text. So that's the only difference there. And can you access this workspace through RStudio Cloud later? Yep. And you'll be able to download a zip file of all of the different files and data and stuff later too. So you can run this all on your own computer. Okay. So the last thing we're going to talk about before we take a break here and then talk about graphic design really quick is how do you actually get these pictures onto your computer? Because right now, everything we've been doing just lives in this it lives right here. And so you could like take a screenshot or save it, but that's miserable. You don't want to do that. So instead, there's a function called ggsave that will save a plot as something on your computer. The way you do this is you have to assign the output of ggplot to a variable. So we make something called myplot. It's going to be ggplot. Here's all of the aesthetics and mappings and everything that we do. And then if you use ggsave, you feed it a file name, and it's smart enough to figure out how to plot it. If you do PDF or .png or .jpeg, it will save it the right way. Then you feed it the name of the object, and then you can give the specific dimensions here with the width and height and stuff like that. And then it will save that object to your computer, and then you can share that with people. So that's how you save graphs here. So again, that was just a few examples of the different layers that you can do with ggplot. There are a billion different other examples. You just have to look at the documentation and just play with it and figure out different things. And the really important part about this is that it's basically a different way of talking about graphs. I mentioned this at the beginning. In Excel, you get this menu here and you have to scroll through and figure out the exact plot that you want. And these are called chart types. But we're not talking about chart types here. With the grammar of graphics, we actually talk about the elements of the chart. And so what you can do is you can describe an entire graph just using this language and you know what it should look like. So if you say map a column to the x-axis filled by a different variable and use geom call to get stacked bars, you can explain that to somebody and they can recreate that same graph. For instance, this right here, we've mapped wealth to the x-axis, health to the y-axis. We used points, we colored by continent, size by population, scaled the x-axis with logs, and faceted by year. That whole sentence there represents this graph, and anybody can reproduce that. Programs that use this grammar of graphics idea, Tableau does this. You could read this sentence to somebody, they could make the same plot in Tableau. Doing this in Excel, good luck getting the points sized by specific columns and faceting. Like that's going to be really, really hard, impossible. Or here, we've mapped health to the x-axis. We used a histogram with bins for every 5 years, and we filled and faceted by continent. And there's our picture. And again, it's reproducible by anybody. Or here, we've used continent on the x-axis, health on the y-axis. We're using violin plots and box plots filled by continent, showing the distribution of life expectancy across the different continents. So again, it's a whole new language for explaining this stuff. And it's a very powerful language. You can do all sorts of really cool things, just adding more and more layers. And you just need to get the hang of playing with it. So let's go ahead and take a break. We have one final question here from Katisha. Can R suggest a best geom based on the observable properties of the data? No. ggplot's not like magic. It can't read your mind. So you just have to guess. But really, all you do is like you get familiar with ways of showing data like scatter plots and bar charts. Those are kind of the foundational ones. But then as you just start experimenting with aesthetics, what I often do is I'll just make a scatter plot with geom point, and then I'll just start throwing aesthetics into it and size it by something and color it by something and facet by something. And then it starts evolving into this really cool complex plot. And that's kind of the best way to do it, to find underlying trends that way. Instead of just having a library of here are all the acceptable plots I can do. We're moving away from that. And instead you're just saying, here's some different geoms. Let's color them and shape them and fill them and do all sorts of things with them and see what happens. And it's a cooler way of getting at the data. Okay, so let's take a 5-minute break and then we'll come back and talk about some graphic design stuff. And during the break, if you have any questions, put them in chat. And otherwise, I'll see you back in about 5 minutes. Okay, so we talked about the grammar of graphics, and now you can describe plots using just aesthetics and mappings and geoms, which is a really cool thing, a really cool new skill you have. So what we're going to do now is, for the next few minutes, talk about some principles of graphic design, which has nothing to do with ggplot. And then we'll combine graphic design principles with ggplot to make really cool, aesthetically pleasing graphs using aesthetics like the design way, not the mapping a variable to a graphical element way. So we care about graphic design because if you're making plots, you want your audience to be able to read the plots and understand the plots. And so you want to think about your audience. And the way we think about audience needs and tailor our things or tailor our designs to their needs is the whole process of graphic design. If you do basic default Excel plots like this, sure, that works, but it's going to be less convincing. It's going to be less impactful if you're trying to tell a story about something. And so we want to be able to care about like our individual design choices, the fonts that we choose, the contrast that we add, the colors that we use. And so having some sort of baseline way of thinking about design is actually really helpful if you care about data visualization. There are, like, this has been hotly debated for thousands of years, what makes pretty things pretty. Basically, like what makes good design. You can get a PhD in graphic design and debate this forever and ever. The easiest way for me to remember this And this is something I do in my own works. I minored in graphic design and I do academic print design and other things on the side. So I do like regular design stuff too. And even then, like the easiest way for me is this acronym here, CRAP. And it stands for Specific Design Principles. And it's basically a checklist you can go through when you see some sort of designed object, whether it be a poster or a book or an ad online or a graph or anything that has designed stuff in it. You can go through this checklist and see if it's well designed and how you can improve the design. So it stands for contrast, repetition, alignment, and proximity. And this all comes from this book here by Robin Williams. It's called The Non-Designer's Design Book. When I teach actual graphic design classes, this is the textbook I use, just because it is like super simple, easy to remember, and it gives you a really strong foundation for making pretty things. So I'd recommend just getting this in general if you want to make pretty things. If you're making posters and flyers for your office and they're really ugly and you're just making things Times New Roman centered big, that's not great. And this explains why, and it explains how to make things better. So what we're going to do is briefly talk about these 4 different principles here and then see how they get applied to data visualization situations, and how ggplot uses these principles, contrast, repetition, alignment, proximity, to make really pretty graphs that are more impactful and more understandable and more accessible. So the first principle here is contrast. The underlying principle here is that if you have 2 things that are not the same, then make them really different, and don't be a wimp about it. And there are all sorts of ways of adding contrast to things that you design. One common way is to use typographic contrast, where you can use contrasting type families. So if you have some sort of memo, for instance, it'll have headings, it'll have a title, it'll have body text. You can use 2 different fonts in there. You can use one font for the body text and one font for the headings. And as long as they're different, then it'll add good contrast and it'll feel better than if it was just Times New Roman all the way through, for instance. To get this difference in type family, what we have to do is talk briefly about what type families are. So if you notice, there are things called serif fonts, and you've probably noticed this before, but like if you look at the letter forms here, there's these little things coming out of the letter forms, like the bottom of the P here, the H has this little flag here. All of those little extra flourishes that are added to the letters, those are called serifs. They were invented 500 years ago with the printing press to help aid with reading. It helps connect the different letter forms across as you're reading the Sphinx of Black's Court. It kind of moves your eye along, so it helps with reading. You can also do sans serif fonts, which are fonts without the serifs, hence the sans. And so if you look at the P here, there's no fancy little flippy things coming out of it. It's just P like that. The difference between serif and sans serif is pretty strong. And so if you had headings that were sans serif and body text that was serif, that's going to be a good typographic contrast. If you use Garamond for your headings and Times New Roman for your body text, those are both serif fonts, and that's not going to be a lot of contrast, and that's going to look like you just made a mistake. And so you don't want to like use the same type or same type family throughout a document or throughout some sort of design, because it'll just not look great. It doesn't have strong contrast. There are other type families. There's slab serif, which is more like a wanted sign from like the Wild West, where the serifs are there. They're just like gigantic. You have script fonts, you have monospaced fonts. So generally the rule of contrast is you just choose 2 of these font families and go with those. And that adds lots of contrast. You don't want to choose 2 slab serif fonts or 2 sans serif fonts in general, because that's not a lot of contrast. So here's an example. These are 2 different fonts. One is Garamond and one is Minion, I think. You can tell just barely, like if you look at the A, the lowercase a, it's slightly different, and that's just like a mistake. But here, one is sans serif and one is slab serif, and that adds a lot more contrast, and it's a lot more impactful and looks cool. There's also contrast in weight. Lots of fonts have different weights to them. You can have extra light, you can have black. So in this situation, you could use the same sans serif font throughout your design, but you just use some things with black and some things with extra light, or some things with semi-bold and light, or some sort of contrast there. This is good for data visualization, actually. You can have your axis labels be light and have your titles be semi-bold or bold or something. it's going to be the same font throughout the whole design, but there's still contrast added in it because of the different weights in the font families. So here's another example. This is a single sans serif font throughout this document here. Here it's the same sans serif font, just different weights. One is semi-bold and one is light, and there's a lot of difference there. It's a lot more impactful. This feels like better designed. All we did was change the weight of the fonts, and it feels better that way. You can use contrast in size. You can have big things, small things. Again, the whole goal here is to not be wimpy. So if you have some sort of policy memo or policy report and your body text is 11 points, and then your headings are 12 point, that's not a lot of size contrast. That's a very wimpy size contrast. So you can do like 11-point body text and like 18-point font or something bigger, like so you can actually tell that you purposely made that difference. It doesn't look like a mistake. You can do contrast in color. You can get a PhD in this whole color theory stuff. It's really complex world. If you go to color.adobe.com, they have a whole system that Adobe has designed for figuring out good color palettes that meet specific theoretical requirements. You can have complementary colors. You can have triad colors. You can have all sorts of things there. And this is just based on the color wheel that you've all played with since like second grade. There are laws of color that figure out what colors are contrasting and not. And so this is a good way of finding contrasting palettes. Another cool thing that Adobe Color does is you can upload a picture and it will extract the most important colors from it and then make them contrast with each other. So if you look at this Atlanta skyline here, these are the 5 most important contrasting colors from the picture, which is really cool. So if I was doing some sort of report about like urban Atlanta, I could include this as like the stock photo, but then I could use these colors throughout the report and it matches the photo and it just like ties everything together and it still has contrast, which is kind of magical. As far as data visualization and color, we had a question about Viridis earlier. When you're trying to see differences in colors in documents, values that are on the color spectrum, we try to assign value to that. And so like blue and green are different, green and red are different, and they're spaced differently along like the color spectrum, but they're not spaced equally along the color spectrum. And so if you have a scale of like 0 to 100, and you want to color everything by 10, so you have like 10 different colors or 5 different colors. So we're going from 0 to 20, 20 to 40, 40 to 60, etc. You're going to want to choose colors that represent that same distance, that represent 0 to 20, like 20 units of difference and then 20 more units of difference. If you just use a rainbow, it's not going to be perceptually that same distance between all of the categories there. Another issue you have with colors is 8% of men and 0.5% of women have some form of color blindness. And so it's very common, especially when you're working with like budgets. If you have some budget system and you want to show that you are under budget, and you could color it as green, and over budget means red because stoplights are green and red. And so that's kind of, we map those colors onto negative and positive. But the issue there is 8% of men have some sort of red or green color blindness, which makes it really hard for people to see the difference between red and green. Stoplights get away with it because red goes at the top and green goes at the bottom. But if you just have a plot with red and green, good luck distinguishing that if you are colorblind. And that's going to be an issue. So instead of just using default colors or thinking about red and green, it's a good idea to use other forms of color palettes that are perceptually uniform and that are colorblind accessible. So here's this rainbow palette, for instance. Notice how it goes from red at one extreme to red to the other extreme, which is not very helpful. It loops back on itself. And so if you have some super low value on a map that is red, eventually it's going to be the same value if it goes super high. You can get around that by like cutting the rainbow palette off somewhere here in the middle. But again, it wraps around itself. And also visually, the distance between this red and this purple is not going to look the same as the distance between this blue and this turquoise here. And so your eyes can't really tell the actual like numeric difference between those colors. If you do something like Viridis though, this is perceptually uniform. The distance between this yellow and that green right there, if that's like X number of units, that's going to look the same as the difference from here to there at the same distance. Also notice how it doesn't loop back on itself. It starts at yellow and goes to dark blue. Same thing with all of the other Viridis scales with magma and plasma and inferno and all of those others. They start at one color, end at a different color, and it's perceptually uniform all the way through. For colorblind audiences, this is what it looks like if you have deuteranopia, which is red-green colorblindness. So notice the rainbow palette, it starts off at this yellowish and it ends again at that yellowish. And here everything's just the same color blue in the middle and the same color yellow. And that's really hard to tell any differences in coloring systems. Down here with the Viridis scale, though, it starts with yellow, ends in blue, and it's perceptually uniform at each of these distances here. Magma does the same thing. All of the Viridis palettes do the same thing. So it's generally a good idea to do something like these because they're more accessible for colorblind audiences, but also more accessible for anybody if you're trying to see exact differences in colors along that palette. If you're just using the default rainbow, it's going to look messy and it's going to be really hard to tell any differences. So a good example of that, here's a map of Georgia. The counties here are filled by area, and so the bigger counties have different colors. This is a typical rainbow palette here, and you can tell like these are probably bigger counties, but then the rest of the map is just kind of blob. Like you can't really tell where the smaller counties are. It might be these orange ones probably, but then it just kind of gets mixed up in this whole rainbow world of non-perceptually uniform colors. Here's that same map, but filled using Viridis. So you can see like there's an actual ranking to the color here. The darker the color is, the smaller it is. The lighter and brighter and greener and yellower the color is, the bigger the county is. And so there's actually a scale to it instead of just random rainbow colors. Same thing here. There's that same Viridis scale, but using Inferno instead of Viridis. It's just slightly different colors, but it's still that perceptually uniform difference across the color palette. So doing something like this adds a lot of contrast to your designs and increases the accessibility of them. And so it's a good idea to think about the colors you're using rather than just the default, any rainbow stuff. That's going to be hard for people to read. If you use these other more accessible ones, then it helps with accessibility. Okay, the second principle is repetition, where you want to just repeat something in the design throughout the whole design. You can repeat all sorts of things. You can repeat colors, you can repeat fonts. So if you do a document, for instance, where you have a sans serif font and a serif font, and you're using your serif font for your headings, then you probably want to use that same serif font for your titles and your subheadings. If you have page numbers, maybe use it for the page numbers or a running header, and then use a serif font for your document. Maybe use the same serif font for footnotes. You just want to keep repeating those same things. Don't add like 13 different sans serif fonts. That's not good. You want to keep repeating the same fonts. You can repeat different graphical elements. If you have like a logo, have the logo in the same spot on each report or something, just to add that repetition. And then you can repeat alignments, and we'll talk about that in just a minute. So if you look at this, here's an annual report from Oxfam, and it has all sorts of cool repeated things. It uses two different fonts. If you notice, the title font is this kind of funky, all caps, the letters are kind of tilted. And then it uses a sans serif font for the rest of the text. It uses the same size for the headings across different pages here. The colors are slightly different. It doesn't repeat that same blue on this page, but it's still repeating color palettes. And so if you flip through the rest of the document, you'll see the same blue and the same green appear in different situations. You'll see the purple maybe mixed with the blue. You'll see this dark maroon red type thing mixed with the green. You'll see kind of that same color palette repeated throughout in different combinations. You also have repetition with the placement of these stock photos. They're all kind of in the same place. The captions have the same style to them. This sans serif font, that size, with the placement of the picture here above top in all caps. So everything on this page is repeated somewhere else in the document, and it ties it all together, and it feels very well designed. So repetition is a good thing to do. Alignment. This principle just says that everything needs to be connected to something else on the page. You can't really have anything just floating around not aligned with something else. So a good example of that is this picture here. This looks nice, I guess. It has contrast, like that's bold and that's light. Yay, typographic contrast. but it doesn't feel very put together, because if you look, like this box here is kind of floating out here, this box is floating somewhere else, this is kind of floating compared to that one. If we want to add alignment, all we have to do is rearrange these boxes to make it so that everything is connected to something else on the page. So if you look at the top of this box, it's connected to that top. They share the same alignment. The edge of this box is also shared with the edge of that box, which is also shared with the edge of these text boxes. So we didn't change any of the fonts or colors. All we did was make sure something is aligned to something else on the page. You can practice this in real life if you just draw lines. So in this instance here, you have 4 different vertical alignments where you just draw a line next to the edges of these things. And here's the other one, forgot to draw that one. And you have 3 different vertical alignments or horizontal alignments. You have this one, you have that one, might as well just move it up so it shares. And then you have this one. So what you can do is just rearrange them so they all kind of share some similar alignments. Now everything is shared here. Everything is shared there, everything is shared there, and it feels a lot more put together because things are aligned and put in place. You can also add contrast to alignment, which is a common thing that people do, and it's another way of adding contrast to your documents, but also playing with alignment. So one very common thing that you'll see is you'll have like centered alignment and then left alignment. That is contrasted, but it's not very strong contrast. That's like using Times New Roman and Garamond. Like they're different, but not super different. And so if you want stronger contrast, you can do something like this, where you have the headings be right aligned, have the text be left aligned. You have 2 different alignments, but you have strong contrast in the alignment. And if you're thinking about repetition, then all of the chapters in this document would also be right aligned. Maybe the title for the document would be right aligned as well. You're going to want to repeat that same split there. So you're basically combining contrast and repetition and alignment all at the same time. And it adds a lot of like design flavor to it. It makes it more accessible and cooler looking than something like this. So that's contrast, repetition, alignment. The last letter we care about is P for proximity. This is the easiest one. This is just group related items together in logical groups. So you can do this with all sorts of different ways. You can group things using color. You can group things using type, using alignment, using white space. You just need to make sure things that should go together are together. So if you look at this fake business card here, looks neat. But if you want to contact this guy, you can't remember his name. Is his name Mermaid Tavern or is his name Ralph? Like you have to go look in that corner and then you have to figure out that's his phone number, I guess. And it's hard to find everything there. If you just rearrange all of those elements so they're in logical groupings, here's his contact information. Here's his business name. There's his name. That's a lot easier to read. It's a lot quicker to read. And so it's better designed because it meets proximity. So what you do with these core graphic design principles is any design thing that you see, like if you're walking down the street and you see some poster hanging up there, you can go through this checklist and see how is the contrast. Did they add some sort of contrast with color or type or alignment or something? How is the repetition? What elements are repeated throughout? Or is there a lack of repetition? Are things aligned? Is there good, strong alignment? Is there contrast in the alignment? And is there proximity? Are things grouped the way they should be? And if you just go through this checklist with contrast, repetition, alignment, proximity, you can improve all sorts of graphic design things, not just the graphs that we're going to be talking about today, but anything that you make from now on. Just go through that checklist, CRAP, and you can make very well-designed things in the future. And these are kind of the core graphic design principles, easiest to remember ways of making pretty things. So applying this to the ggplot world, you can actually make it so that your plots that you make follow these same principles. You want to have good contrast, repetition, and alignment and proximity in ggplot plots. And the way you do that is with the theme function. And that lets you target specific elements of your plot. So if you want your subtitle to be light and your title to be semi-bold, you can do that. You can use the theme function to target those specific parts of your plot to make them those different font weights. If you want your title and your plot to be right aligned and everything else be left aligned, so you get good contrast in the alignment, you can also do that with the theme function. The only issue with theme is that it is the most complex function in all of R. It has 94 or 95 possible arguments that you can feed to it. And nobody has them memorized. Not even like the author of ggplot knows every single thing in there and remembers every single thing in there. It is impossible. So what people do, smart people, have gone and made pre-made themes that already have a whole bunch of good, sensible presets. So there's this library here called Harbor Themes, where all you have to do is use this theme ipsum ps. This is going to be theme ipsum is his whole world of nice themes. If you notice, his axis labels are all aligned to the edges there. So you don't have a centered alignment and edge alignment because he's trying to apply that principle of contrast there. You don't want to have center and left because that's not very strong. But if you have left and right, that is much stronger. So he's pushing everything over to the sides for the sake of alignment and for the sake of contrast. PS is just the name. It's the acronym for the font that he has. He has a whole bunch of different fonts that are embedded. So there's also one called this is Plex Sans. If you look, he's got a whole bunch of other acronyms that are for different fonts that you can add. And we'll play with this in just a minute. Here's Roboto Condensed, but he has a dark version of it. But again, that's a slightly different font. But this looks a lot better than that theme dark that we saw earlier, just because of the contrast that this guy added to his theme here. You can also have themes that look like specific publications. And so here's the Economist's theme. So if you want to make a graph that looks like it came from the Economist, you just add theme Economist and it will do it. And notice here, we added scale color Economist, and that made it so it uses the Economist's color scaling instead of the Viridis scale or the Rainbow palette or whatever is using the Economist version. You can even get super artsy like this. This is a fun package called ggplot, where you can do like fancy cursive writing, and these colors look really cool. That looks fancy. Put that in a report. That would be neat. So what I want you to do is take the next couple minutes. We'll do 3 minutes. If you go to the second document in the files panel here called themes, and scroll down to the first your turn, I have a plot here that is back to our penguins plot. It's got some titles and subtitles and other things added to it. I have theme BW. But what I want you to do, that's black and white. I want you to spend the next couple minutes experimenting with different themes. If you notice at the top, I've loaded 3 different packages that just have a ton of themes in them that people have made. You can either Google like TV themes or Harbor themes or GG themes and see all of the ones that are available. Or if you just replace theme BW here with theme underscore, and it should bring up this list, we can do theme Brooklyn Nine-Nine. And here is somebody designed something that looks like it came from the TV show Brooklyn Nine-Nine. So just take a couple minutes and experiment with these different themes and see what's in there. I think there's a theme Stata. Yep. Yeah, now it looks like we did it in Stata. So take a few minutes, play with that, and come back and we'll... Yes, the autofill comes only after you run. So make sure you run this first chunk up at the top, the setup chunk. So it loads those libraries. And then the autofill should show up. And again, if you just Google TV themes R, you should see this guy has a list of all of the different themes. There's a SpongeBob theme, Simpsons theme, Game of Thrones theme, or more serious, if you go to GG themes R, there's all of these. Excel and 538 if you want to be like them, Economist, Wall Street Journal. Okay, so hopefully you found some cool themes there. The TV themes are fun, making a Simpsons plot, sure, that's neat. But in real life, what I typically do is I will use something like theme ipsum. The themes from this Harbor themes package, those generally I find are very well designed and a good base that you can work with and make little modifications after that. So if you notice, if you look at the documentation here, this theme Ipsum ES is for, it uses Econ Sans, which is the Economist's font. PS is IBM Plex Sans, which is a sans serif font. Public Sans is a different one. Roboto Condensed is a different one. And then Titilium Web is also a different sans serif font. So those are just kind of all built-in fonts to these themes. So living with like the theme Ipsum ones is generally kind of the easiest way. So if you do theme Ipsum Roboto Condensed, that looks great. So cool. So it also meets all of the classifications or requirements for crap. We have good alignment. So the title here is aligned with the edge of the plot. Everything is left aligned except for the axis titles, which are right aligned, adding the contrast. Repetition, this is the same font used throughout, but we also have a deeper or a thicker weight here for the title. So back to contrast there. Proximity, things that should be together are together. The legend is over here. It's not kind of spread out somewhere else. And so it kind of meets all of those checkboxes for contrast, repetition, alignment, proximity. How do you fix the title cutting off? Good question. One, you can resize the image. If you click on this little icon at the top of the plot, it will pop it up into a new window. And so then you can kind of resize this and make it shorter and wider, and that would work. If you're using ggsave to save this, then just make sure you have a wider width. So you say width equals 8, height equals 5 or something. So that way it's wide. If you want to add a line break so that it says penguin build depth gets bigger and then have a line break as penguins grow heavier, the way you do that is you do a \n. This right here adds a new line is what that stands for. And so it looks goofy because it looks like bigger NAS, but really that N will just add a line break. And so now if I run this, it says penguin build gets bigger, line break as penguins grow heavier. And so that fixes it. Okay. So those built-in themes are great. You can do all sorts of tinkering stuff. The whole theme system is incredibly complicated. It has 94, 95 different arguments you can use. You can target every possible element of the plot. In the cheat sheets folder in the RStudio project, I have a PDF there of this picture here. And it shows you basically like if you want to change the space in between these facets, then you would use this panel spacing argument. If you want to change the ticks and have them be dotted instead of dashed, you can do that with axis.ticks. You can target every little tiny possible element here. And it gets really complex. You can have simple things like plot title, panel grid, legend background, stuff like that. But you can also get hyper specific like axis, ticks, length, x, bottom. That will target just the axis tick lengths on the bottom x-axis, not the top x-axis if you have a second x-axis. And that is really hard to use. So what I typically do is I just use one of the pre-made ones. And then if I want to adjust, I then add a theme layer after it and maybe move the legend to the bottom or something. And the way I figure out how to do that is I've been doing this long enough that I know lots of the parts of this. I still don't have this all memorized. It's impossible to do that. So I'll refer to this and say, I want the spacing between the panels to be a little bit bigger. I look up how to do it, and then I add that after theme Ipsum, whatever. There's also an add-in to RStudio that lets you basically get a menu system that will generate the code for you for changing specific elements of the plot. So if you want to just change one of the axis ticks to be dotted or have the background be a certain green color or something, you have this ggplot theme assist or ggtheme assist. So if you use the slides and click on that link, it'll take you to the help page for it, and it'll show you how you can use this. And so this generates the code for you, and then you can include that in your plot. So it's a good thing you can do that. Cool. So that is basically the graphic design stuff here. We won't do this your turn thing, but let me just show you how you would use this theme. So if we want to use the theme to make the title bold, to make the axis titles left aligned and bold, put the legend at the bottom, remove the minor grid lines, so the grid lines in between the axis ticks, we would use the theme function here. So we're using theme black and white. That's just kind of the base theme. And then we're going to say plot title, make it be bold. The axis title, make it be left aligned and bold, make the legend be at the bottom, and then get rid of the panel grid, minor grid lines. And so that's basically how you do themes. It's incredibly complicated. There's no way we can cover it all today. When I teach this as a class, we spend a whole class session just on the theme function. And even then, it's impossible to cover everything that it does. So really, you come across it when you want to make changes to something in your plot, and then you go to Google and say, move legend to bottom ggplot, and figure out how to do it. But and the GG Theme Assist is also a really helpful way of doing that. And so that's just kind of some cool resources you can use to apply these core graphic design principles, contrast, repetition, alignment, proximity, to your plots and make them prettier and more accessible. So that is graphic design applied to ggplot. So go ahead and take a 2-minute break. We'll go really quick here. And then we'll do the final section here about animations and interactivity and making interactive HTML plots and making movies of our plots. So come back in 2 minutes and we will resume the final part of this and ask any questions you come across in the chat. Okay, welcome back to the last section of this. This should go fairly quickly because I'm not showing you detailed ways of doing this. It's very complicated to do these animations and interactivity. So I will point you to the resources to be able to do this. But this is mostly just showing off what you can do. But before we start, there is a question. Is there a protocol for giving credit to these theme packages and published work? Kind of, but not entirely. The whole R world, all of these packages that you're using are open source. And so people make them and make them available, and anybody can do whatever they want with them. And sometimes you can give credit, sometimes you don't. It's good practice to, like, if you're doing some academic work, you can cite the packages that you use. So often you'll see people cite like ggplot in general, and you can look up how to cite ggplot. There's a billion different ways. You just have to Google it. But themes like theme ipsum, etc. If you have room in your bibliography, you can cite the Harbor themes thing, but most people don't. And you just the people who make these packages realize that they're providing a public good and they won't get credit for it, and that's fine. So if you want to be super cool, cite these things, but you don't have to. Okay, so animations and interactivity. We're going to talk about one way of doing animations and then 3 different versions of interactivity you can do with graphics in R. So animations, the easiest way to do this is there's a package called ggAnimate. I think its URL is just gganimate.com. If you go there, you'll see all sorts of documentation and examples of how to do this. The underlying concept with ggAnimate is that you're basically taking a variable in your data set and mapping it to the animation aesthetic. And so in the case of Gapminder here, this is Hans Rosling's thing, but this is now faceted by continent. And so it's the same code that we're used to. Here's Gapminder. Here's our mappings of the different columns. Here's geom point. We're changing the scaling of the size of the points. We're using a log axis. We're faceting. So these are all the layers we kind of looked at before. And then these last 3 layers are special things that come from ggAnimate, where we're adding a title, but we're putting the frame time in the title. So notice it's going like that's ticking upwards. This transition time layer is just saying, take this year column and use that as time. And so it's just moving through the year column and showing the changes in the data there. And then this ease AES is just making it smooth. If we didn't have this ease AES, it would just, like, this is every 5 years. And so it's really just interpolating the data. So you would see really chunky movements. But this ease AES is just saying, make it a linear smooth as it's going up. So that's ggAnimate. If you look at the animations interactivity, our markdown file for today, and run the very first chunk here, it should load the ggAnimate package and the plotly library or package. So if you scroll down, we're going to make a quick animation of our penguins data here. So if you notice, this right here is just going to be our normal penguins data that we've been working with. This last section is the special ggAnimate stuff, where instead of doing it by time, we're going to do it by category. So it's going to animate each of the different species. It's going to loop through all 3 species and basically show the points based on that. You can change all sorts of settings here. We're going to make it so that it shows it for 1 second and then has a quarter of a second transition to the next species. That's all manipulatable. This, I have none of this memorized. This I figured out by looking at the documentation at ggAnimate.com and following the different examples there. Every time I make an animated anything, I do the same thing. I have 1 page up with all the documentation, and then I figure it out. So don't feel bad doing that. Like, you have to look at the documentation. So if I run this, what it's going to do is it's going to render it. It takes a little while. It's going to take about 4 more seconds here. So really, it's just making like 100 different plots. And then here it's stitching them all together. And then it should create a plot that looks like this. So here's a second of the species, and then it transitions to the other species, and then it transitions to the other species. Neat. We didn't add any of the easing there, so that's pretty chunky. It's just like there, there, there. If we add transitions here, make it fade out and shrink as it exits, it's still going to show the same animation, but now it's going to look fancier. So we just wait a couple seconds for it to render and stitch everything together. And there it goes. So now it's going to sit there for half a second, and then it's going to fade out. So there's our chinstrap penguins. There's our Gen 2 penguins. That is so cool. So ggAnimate is like really fun. You can save these things as animated GIFs. You can save them as movie files. It is entirely possible to make an animated graphic and then stick it into video editing software like Premiere. That's basically what Hans Rosling did to make his video. He just did that before ggAnimate was a thing. But if he had made that video today, he most likely would have used ggAnimate to make those dots and then control it with video editing software. So that is ggAnimate. Super brief introduction to it. It is incredibly complicated. You can do really cool things with it. I recommend just playing with it. Really, the only technical difference between it and the rest of ggplot stuff is it's just a layer that you're adding, and you're just mapping one of your columns to the animation aesthetic. But everything else up above is regular ggplot stuff that we've been looking at. Okay, interactivity. There are 3 general ways of getting interactive plots with ggplot. You can do single plots with a package called Plotly, and this is actually incredibly easy and really like powerful. You should do this all the time just because it's neat. You can make dashboards with something called Flex Dashboard, and you can make whole interactive apps with something called Shiny. And we are not going to talk about Shiny. You can take a whole course in Shiny to get this because it's really hard. So yeah, what we're mostly going to show is Plotly, and then this idea of a Flex Dashboard. So before we move on, one more question from Jonathan here. If ggAnimate is a layer, what is ggplot called? It's a good question. Nobody has an official term for it. I like to just call it like the foundation. So like ggplot, the actual function there is just kind of the base, and then you're adding everything onto it with all of the geoms and scales and labels and themes and animations. So that's kind of what I use, but other people will call it different things. Okay, so interactivity. Plotly is the easiest way to do this. Plotly is special software that people have written that make animated HTML plots with JavaScript. Typically, you have to know JavaScript to make these things. And I don't know JavaScript, and I've played with it a few times, and it's miserable. So with Plotly, though, you don't need to know any JavaScript. The ggplotly package will translate your R code into JavaScript for you and make an animated graph. So if you look at this, for instance, here's Gapminder 2007. Here's our ggplot code. This is all just normal ggplot stuff with geom point. We're mapping these things. We have a logged x-axis, and we're using this minimal theme. And I stored it as an object called myplot. The only thing I have to do to make it interactive is I feed myplot into this function called ggplotly. And now if I hover over these points, this is interactive. And like you can see what these different actual values are in the continents. That's just an interactive plot. I can zoom in on specific areas of the plot. You can do all sorts of really cool things with this. And I didn't like the only code I had to use was ggplotly. You can control what the tooltips show if you use this text aesthetic. Normally, there is no such thing as a text aesthetic, and if you try to run it in R, it will give you a warning and say, what is text? But Plotly knows what to do with text. And so if you say text equals country, now if I hover over these things, you can see the actual country name. So there's El Salvador, there's Egypt, there's South Africa, there's Gabon. You can see all sorts of stuff right there. So if you want to see how to do this in RStudio, go ahead and scroll down to the Plotly section, and you can run that same code. So if I click on the play button here, it'll make a smaller data set called Gapminder 2007. It'll make a plot called my plot. And then we just feed that into ggplotly, and you'll get it down in this viewer right here. And then you can zoom in, you can do whatever there. Can ggplotly make animated graphs? No, it cannot. It would be really hard to do that anyway because the dots are going to be moving. And so you like I've seen it in real life, like having an animated interactive plot. But in order to do that, you need like a play button so that people can pause the graph and then hover over stuff. And Plotly does not do that. You'd have to write your own JavaScript to do that, and so that's miserable. So yeah, that's the code here. If you look at the last chunk here, this just shows how to get the text in there. So if you hover over it, you can see where Niger is and Syria and Taiwan and all that stuff. So that's how you do interactive plots. It's really ridiculously easy. And it's really powerful when you show this to people. They're like, whoa, so do that and show off your skills. It works with pretty much any geom. Like the histogram, I can hover over the histogram and it'll show the values, like how many are in. There are 9 values in that bin right there. You can also save it as an HTML file so that you can email it to people. This function right here, save widget, it works just like ggplot, but for HTML things. And so you can save your plot as this HTML file and then put that on your blog, on a website somewhere, email it to somebody, and then they have access to it. The documentation for it is incredibly well done. It's got 1 billion examples. So every time I make an interactive plot, I Google ggplotly, and I have like 6,000 tabs open for examples of how to do stuff. And then I tinker with it until I have a really cool looking plot. So that's how you do it. So if you want to make dashboards, though, which are entire websites with many interactive plots or other text that is included in them, there are packages that let you do this. There's a package called Flex Dashboard that lets you combine a whole bunch of plots into a single website. And it's really cool because it's basically using R Markdown. So you're just writing regular plain text here. So if you want chart 1 and chart 2 to show up as like this system here, where if you have a whole web page and then you have one row with chart 1, one row with chart 2, you just put code in here and it'll go in chart 1. You put code in here, it'll go in chart 2. They can be static charts, just regular ggplot things. They can be interactive charts. So you hover over it and it shows stuff. And that's basically how you make a dashboard. You just put charts in here and knit the document, and it turns into a self-contained HTML file with stuff in it. You can arrange them. The documentation for Flex Dashboard shows you how to get the different kind of templates and the different layouts. You'll see this all over the place now, especially with COVID-19 happening. Pretty much every state agency that shows COVID tracking uses basically Flex Dashboard and uses these animated graphs that we're playing with right now with Plotly. You can add all sorts of fancier things like big numbers. You can have like these gauges down here. There's a whole bunch of different examples. If you go to the Flex Dashboard website, they show different things there. So here's like NBA scoring in the 2008 season. You can hover over this heat map here and it'll show you all sorts of details. It shows you a table of all of the different statistics there. Utah, their COVID tracker is built in Flex Dashboard. I think Georgia's is something similar. California has something very, very similar, but this is all just like ggplotly and Flex Dashboard. And this is an R Markdown file that they just knit every day and it turns into a dashboard, which is really cool. Again, the documentation is fantastic. Just look at it and it walks you through all sorts of examples of how to make these things. So I'd recommend just playing with it. Final thing, you can make complete interactive apps with Shiny. Shiny is incredibly complex. It's like almost a separate programming language that uses R to make things interactive. The only difference between so with these dashboards, these aren't super interactive. Like if I wanted to switch to just one county, um, there's no way to interact with this, to zoom in on one county specifically. To do that, you would need something like Shiny, which would redraw the maps if you chose one of these counties, or it would redraw the maps if you chose a different statistic. Instead of showing cases, you wanted to show deaths or hospitalizations or something. There's no way to get that with kind of this static dashboard here. Shiny lets you do that. It's way more complicated. I've never actually made a standalone Shiny app all by itself, and I have no intention of ever doing it because it is hard. But you can actually incorporate some of the Shiny type things into Flex Dashboard and make it a little bit more reactive. So you can choose specific variables, for instance, and it'll refresh the page. So that is possible. You can do Shiny type things with Flex Dashboard. Again, RStudio has tons of documentation. They have like a 32-part class of how to make Shiny apps. Go through that if you want to. It's complex. But you can do really cool things. So if you look at this, this is somebody's published paper from biology. You can change all sorts of different parameters here. You can rerun models. You can run whole regression models in your browser using Shiny. COVID trackers also use this. California's COVID tracker is actually formally a Shiny app. It's not Flex Dashboard. And so pretty much every COVID tracker out in the world either uses Flex Dashboard or uses Shiny or something very, very similar. You can do all sorts of stuff here. This shows you all of the Lego pieces ever made. You can sort them by color. You can sort them by all sorts of things. And again, you just click on these drop-down menus and it will redraw the image in your browser, and you can do all sorts of analysis there. Flex Dashboard can't do this because, again, it's rerunning the data every time you click on one of these things. Flex Dashboard is just a static thing. All the data is already there. You can kind of hover over stuff, but that's all you can really do with Shiny or with Flex Dashboard. With Shiny, it lets you do fancier things. And again, you can do some Shiny type things in Flex Dashboards. This is a dashboard I did for a project where we have the ability to switch to different models, but we didn't write any of this in Shiny. This is just our markdown with little ggplotly things shoved into different squares. So it was a little bit more complicated, but it's not as complicated as like full on Shiny, scary stuff. So my recommendation for you is to just play with this. You've already seen how easy it is to make an interactive plot using just ggplotly. To get this in a dashboard, you just copy this code and stick that in a chunk in the dashboard so it goes in that corner. And if you look at the documentation for Flex Dashboard, it'll show you how to get all sorts of different layouts, and you can make your own dashboards super simply. And you can do all sorts of really cool things with ggplot. So moral of the story is just play with this stuff. That's the only way to learn it, is to just say, I have a graph. I want to either recreate it, like some ugly graph in Excel, remake it in R using ggplot. Or if you come across some data, just start throwing different aesthetics at it and mapping it to different parts of your graph and facet it, animate it, do all sorts of fun stuff, and just play with it. That's the way you're going to learn all of this stuff. So that's kind of what I have. So if you have any questions, feel free to ask in the chat. Again, all of this will be available in this workspace here. Tyler will also email a link to a zip file that has all of the slides and code and data and everything that you can run on your computer in RStudio, and just play with it. Use this as a resource and have fun. So thanks, everybody.